In this video, we'll talk about the concept of heat capacity. You arrive home on a cold winter day. As you're getting in the door, your dad dishes you a bowl of soup, but you get distracted for a few minutes, and when you come back, it's already cold. Well, no problem, you prepare yourself a new bowl from the pot sitting on the table. Why is the pot still hot, but your bowl is cold? Before you take your first bite, you blow on the spoon to cool it down. Well, why don't you blow on the bowl instead? You check your messages. Your best friend who lives in Kelowna mentioned that their fish pond finally froze over, and that they were out on the boat fishing that day. Why is the pond frozen but not the lake? Also, why is Kelowna so much colder in the winter compared to Vancouver, but in summer it's so much hotter? That night, your bedroom's pretty cold, so you heat up the water bottle and bring it to bed. But why do we risk leaking water in bed? Why don't we just heat up some rocks and put them in a fluffy bag and bring them to bed instead? All of these phenomena can be explained, at least partially, by heat capacity. The definition of heat capacity is the amount of energy required to increase the temperature of a substance by 1 degree Celsius. Now the symbol for heat capacity is C, and the units are joules per degree Celsius or degree Kelvin. And it's typically used in the formula Q equals C delta T, where Q is energy measured in joules, and delta T is temperature difference measured in degrees Celsius or degree Kelvin. From the formula, we can see that if the temperature change increases, the amount of energy required for the temperature change also increases. An example of this is heating up a bowl of soup that was in the fridge. That would require more energy than to heat up the same bowl of soup that had been left on the counter. Similarly, it would require even more energy to heat up a bowl of soup that had been frozen than either of the other two. Also, if we increase C, the heat capacity, we also increase the energy required for the same temperature difference. And an example of this is heating up a bowl of soup versus heating up a whole pot of soup. The pot of soup has higher heat capacity, so it'll take more energy to bring it up the same temperature as heating up the bowl. One limitation of heat capacity is that it depends on the quantity of material you're trying to measure. For example, if you want to know the heat capacity of your water bottle or the jug of juice in the fridge, you won't find the answer in a textbook. Another limitation is when comparing different materials. Which has more heat capacity, 20 kilograms of steel or 5 kilograms of water? Well, there's more mass of steel, so there might be more heat capacity, right? Well, in reality, we can't know unless we compare them on an equal basis. For example, 1 kilogram of water versus 1 kilogram of steel. This problem brings us to the concept of specific heat capacity. We define heat capacity as being the amount of energy required to increase the temperature of a substance by 1 degree Celsius. Specific heat capacity is the amount of energy required to increase the temperature of 1 kilogram of substance by 1 degree Celsius. Our formula for heat capacity was Q equals C delta T. The symbols for heat capacity and specific heat capacity are both C. This can cause a lot of confusion. However, there is a difference. Heat capacity is denoted by capital C, and specific heat capacity is denoted by lowercase c. In order to differentiate the two, I'll write specific heat capacity in red. The units for specific heat capacity are joules per kilogram degree Celsius. Now, much of the formula is the same. Delta T in degrees Celsius remains the same. And energy, Q, in joules, is also the same. We can see from unit analysis that this equation is missing something, and that thing is mass, measured in kilograms. The difference between these two equations is on the top, heat capacity, capital C, and on the bottom, specific heat capacity multiplied by mass, or mc. In fact, these two are equivalent. Heat capacity, capital C, is equal to mass multiplied by specific heat capacity. A unit analysis also shows this equivalence. Now that we've defined specific heat capacity, how do we know the specific heat capacity of various materials? Well, in general, these are available in textbooks or on various websites, but they can also be determined experimentally. And that's more fun, so let's do that. In this experiment, we'll take 4 different substances with presumably different specific heat capacities. In order to have a fair comparison, we'll measure each of them to be the exact same mass, starting with 400 grams of rock. We'll put that in the oven at 210 degrees Fahrenheit, which is the closest our oven gets to 100 degrees Celsius. Next we'll get 400 grams of wood. We'll bake that also at 100 degrees Celsius. And next, 400 grams of steel. And finally, 400 grams of water, which we brought to a boil to achieve the 100 degrees Celsius required. Each of these substances will be added to 300 grams of water, which has been refrigerated down to 5 degrees Celsius. First, we'll pour the cold water into our insulated container. We'll change camera angles and show each experiment side by side. We'll give it a little bit of time to equalize the temperature so that all of the thermometers read 5 degrees. The next step is to add our substances at 100 degrees Celsius, 400 grams of each. Now the video on the far right, the wood, is actually sped up significantly faster than the rest. And this is because it took almost 2 minutes to get all of the wood into the container. During this time, the wood may have cooled off a lot. This may cause us problems later. Now that everything's inside, we'll cover it with our insulation and give it some time to equalize the temperatures. And in fact, we can notice that on the left, the water has achieved its equilibrium temperature very quickly. In the other experiments, this process was much slower, so we opened them up and stirred them around to achieve equilibrium temperature. Finally, the steel mixed with water, the rock mixed with water, and the wood mixed with water achieved their equilibrium temperatures. Using the known values for specific heat capacity for each of these four materials, we calculated final temperatures and compared them to the actual experimental final temperatures. Take a few seconds to pause this video, look at the results, and try to think of why the actual final temperatures were different from the calculated final temperatures. Remember how it took about 2 minutes to get all of the wood into the container? We think that might have caused an error. So, we ran the experiment again for the wood. Instead of putting the hot wood into the cold water, like for the other experiments, we put the hot wood in first and poured the cold water over top. But that wasn't enough. We had to pour the water out and then pour it back over the wood again multiple times in order to achieve an equilibrium temperature. In the first experiment, the equilibrium temperature of the wood was 23.5 degrees, and in the second one it changed to 37 degrees, much closer to the calculated value. That concludes this video on heat capacity. Pause the video and take a few minutes to answer the following questions to test your understanding. And thank you for watching.